Okay, so welcome all. In this particular video, first I will demonstrate or I will explain what is the problem that we are addressing, and then the problem is how to design a digital filter using Matlab. And first I'll set up the problem, and then we will switch to Matlab and see how we can design a digital filter in Matlab. So the problem setup is we have a measurement device which is affected by noise, which is very common, and the signal, which is a noisy signal, need to be filtered out using any digital filter. So what is the digital filter which can filter out the particular noise is what we are designing in MATLAB. So the signal is in continuous time domain x of t, and in order to give the signal to the computer or to the digital filter, we need to use some sampling techniques. So let's assume capital T to be the sampling period, and we know that by Shannon's sampling theorem what must be the sampling period. And so we obtain the discrete equivalent of the continuous signal, which is still a noisy signal, but it is in a discrete domain. And this noisy signal is given to the digital filter, so that the digital filter will perform the filtering operation, and we will get the filtered output as the output of digital filter. So for ease of understanding, let's assume that the noisy signal to be of this particular form: x of t is equal to a sine 2 pi 10 t plus a by 10 into random signal. So this a can be some magnitude. I'm not specifying any magnitude. You can take this a as your roll number. And here you can see that the signal is a sine wave with a frequency being 10 hertz. F is equal to 10 hertz because it is to omega sine omega t. Omega is equal to 2 pi f. Here f is equal to 10. And so the second part, this part is basically the noisy signal part. So noisy signal part can be taken as something significant. So you can take it as a by 10 into a random signal. So we will see how to define this random signal in MATLAB, and uh, yeah, so that is about the signal that we'll be dealing with. And what we are trying to do is, if you are given with such a noisy signal, so this is the noisy signal. If you are having such a noisy signal, how to design a filter which will filter out the noisy part and give us the actual signal in that. Okay, so please remember that in actual practice you will not be provided with x of t, but rather you have the measurement from the device, which already contains some noisy signal. So in order to simulate, or in order to see how this digital filter work, we are actually using this noisy signal x of t. So please remember that this is not the actual case. In actual case, you just have the signal. It may be noisy, it may contain some random signal, and we want to extract the actual signal from the noisy signal. So here we are using this x of t, and we know that the first term is the actual signal and the second term is the noisy signal. Okay, so please keep that in mind. And let's take the sampling period to be 2 milliseconds. So it is 0.002 seconds, and from that we can find the sampling period is 2 millisecond, and so the sampling frequency, which is given by 1 by capital T, it is 500 hertz. So we can see that this sampling frequency is satisfying the Shannon sampling theorem, which tells that we need the sampling frequency to be at least twice that of the highest frequency contact. Okay, so this is the problem setup. So the problem is, if you are given if you are having a noisy signal, some signal, how to extract the original signal, the actual signal that you want, and how to filter out the noise from that particular signal. And so in MATLAB, what we will do is we'll first define this noisy signal. Then we'll try to plot the noisy signal. So what all things we will do in MATLAB is, I'll just list out for easiness. So we will plot the noisy signal and the plot the noisy signal in time domain as well as in frequency domain. Okay, so plot the noisy signal in time and frequency domain. So in order to plot in frequency domain, or what are the frequency components of the noisy signal, we will use the FFT algorithm to obtain the frequency transform or Fourier transform. So we'll plot the noisy signal first in time domain and we'll try to get the Fourier transform as well. Second, we'll try to design the filter such that it will filter out or it will give the original signal and filter out the noises using a filter designer. So this is the app that we are going to use to design the filter. Once we design the filter in filter designer app, we will take the design to the original program and we'll find the filtered output. Okay, so you will find the filtered output using the designed filter, and from that we will plot the filtered signal. So we will plot the filtered signal both in time and frequency domain. Both in time and frequency domain. So this is the agenda for today. So first we will try to plot the noisy signal and in time and frequency domain. Then we will try to design the filter. It may be an IIR filter or an FIR filter. So I am not going into the details for the moment. We'll see how to design a filter in using filter designer app in Matlab, and then we will take the design filter back to the workspace and we'll plot the filtered output in time as well as frequency domain and check whether we have obtained the required signal. Okay, so let me switch to MATLAB since the problem is clearly defined. I am using the online version of MATLAB. So you type in matlab.mathworks.com and log into your MathWorks account. Then you can take a new script and write the script. So right now I have already written the script for you uh, to save some time, and I'll first go through this script, and then we will go to the app for designing the filter. Okay, so this window is the script, which is the M file. On the left hand side you have the current folder, below you have the workspace, and this is the place where the variables are being stored, and at the bottom we have the command window where we can see the output. Okay, so let me quickly go through the code. Here I have defined the sampling frequency as 500, which we have already defined in the problem. The sampling period can be defined as 1 by fs. So we'll get the sampling period, capital T, and k I am taking it as the sampling instance. So sampling instance is varying from 0 to 1 with the time period of capital T. So that means you are having the instances 0, the next instant being 0 0.002, 0 0.004 and so on up till 1. Okay, so that is this k, and this capital A I am defining as the amplitude that you can take as your roll number. So these are the things you need to define initially. Now I am defining the signal x. Okay, so here in this line I am defining the signal. So I have mentioned that the signal is x of t or x of k is equal to a sine 2 pi 10 t plus a by 2 into a random signal, or a by 10. That is better. Okay, so here a is 10, sine 2 pi 10. So here frequency of the signal I have taken it as 10 hertz. K, so instead of t we have taken the sampling instance, so it is k plus a by 10. So I am defining the magnitude of the noise, and I have used a function to generate random signals. So RANDN, random is the function to generate random signals in Matlab, and the random signals is of the size of the sampling instances. So I've used I have used a random function to generate random signals of size sampling instance. Okay, so this X will generate the signal. Okay, so suppose you want to see the plot. So let me check if I can run up till here. So evaluate selection in uh, or rather what I'll do is I'll try to comment the remaining things. Okay, I am commenting the remaining stuff for the moment. I'll explain it later. And now let me try to run it. Okay, so you can see that the workspace is being loaded with capital A 10, F as the sampling frequency as 500, K as the sampling instances. There are 501 sampling instances. Capital T is the sampling period, which is 0.02, and X is the signal. Okay, so now let me try to plot the signal using the command window. So plot K, comma X. Okay, so I'm just trying to plot K comma X. Now you can see the figure which is coming on the right side. So you can see that it is a distorted sine wave. For the moment, let me take off the noise part. So I have commented the noise part just for sake of understanding, and let me run it once again. And yeah, so I'll try to plot the signal now. Plot K comma X. So now you can see that this is a pure sine wave with amplitude 10 and the frequency is 10 hertz. That means 10 cycles per second. Okay, and because of the addition of this second part, it becomes a noisy signal, and that's why it is having a lot of disturbances in the signal. So let me try to plot it once again. Plot K comma X. So you can see that right now it is a very noisy signal. What we would like to do is we would like to design a filter which will take out the noisy part and give us the original signal. Okay, fine. So in order to see the magnitude spectrum or the frequency spectrum, we will use the Fourier transform. So let me go back to the code. So I have used the command FFT to find the Fourier transform of the signal. So FFTX will calculate the Fourier transform of the noisy signal. And in order to plot the frequency spectrum, we need to define the x-axis of frequency spectrum. So for that we use a function of lin space. So it is linearly spacing the points. So I have taken the x-axis of a frequency spectrum ranging from 0 to capital Fs. So Fs is the sampling frequency, and I'm dividing the points with the length of the frequency uh, frequency spectrum or the Fourier transform. So lin space 0 comma Fs comma length FFTX. So FFTX is defined as the FFT of the signal. Okay, so now let me try to run this much and let me try to plot the frequency spectrum. So in order to plot the frequency spectrum, what you can do is plot the x-axis is F, and what is the y-axis? Y-axis is FFT, and what we need is we need the magnitude of FFT, okay, which is given by the function absolute value of FFT underscore X. Okay, so this absolute value of FFT underscore X will give the FFT of the magnitude of the FFT, and let me try to plot this. So you can see that the figure comes, and so x-axis is varying from 0 to 500 fs, and you can see that so this is the noisy signal. That is why it has these grains in this region, and there are two spikes. So please refer what is the Fourier transform of a sine wave. You can see that there are two pulses like this, and if you expand, yeah, let me try to zoom it for you, or rather first I'll do is I'll remove the noise. So I have removed the noise, and now let me try to run it first, and now I'll plot the frequency spectrum so that the disturbances will be out. So now you can see that there is no disturbance in the frequency spectrum. It is only two spikes, and these spikes are at 10 hertz. Okay, so if you zoom it, so let me try to zoom a little bit here. Okay, I'll try to zoom it further. You can see that this spike is happening at 10 hertz. Similarly, the second spike is happening at 10 hertz from the end. Okay, so that will be at 490. Okay, so you can refer the textbooks for the reason of that behavior. Okay, so this command will give the frequency spectrum. Okay, fine. So what I have done in the code is I have plotted the both the signal as well as the frequency spectrum together by using subplot. So I have used figure 1 to name first figure, and you have used subplot. So I am not explaining the subplot command. You can refer to understand what are subplots. So it is basically plotting both of these signals. That means the plot of noisy signal, which is plot k comma x, and the magnitude spectrum of noisy signal is being plotted together. So let me try to run this. Remember, we have removed the noise for the moment. So if I run this, you can see that both the figures will come one after the other. The top one is the original signal without noise, and this is the Fourier transform or the magnitude spectrum. And now let me introduce the noise part as well, so that you will see the difference. Now I am running it. So now you can see that the first signal is noisy, and here below you can see that the main frequency component it is there, but there are some other frequency components which is coming in between those 2 points. So what we want the filter to do is the filter must keep these two spikes, and it must eliminate the remaining things in the signal. So this is only possible if you transform the signal from time domain to the frequency domain. So we will not be able to identify the noise from the time domain, but the good part is we will be able to separate out the noise part if we convert it into the frequency domain. Okay, so in order to do that, now we will go to the application for designing the filter. So in order to take that, we will go to the apps tab at the top, and we will search for filter designer. So you will see that the filter designer app is here. So click on that, and it will open up a new window which helps in designing the digital filter. Okay, so this is the application for designing the digital filter. Here you have, so I'll just mention quickly what is the overall layout of this designer app. On the top, yeah, here you have the current filter information, which is for our information: what is the structure, what is the order, is the filter stable, and so on. And on this tab you have the filter specifications. Here we will see the what are the specifications that we need to specify. And on bottom left is the response type. So this is the important section where we must define what is the type of filter that we are designing. Is it a low pass filter, it is a high pass filter, is it a band pass filter, band stop filter, and so on. And there are lot more options for low pass filter as well, low pass and high pass. Okay, So we need to decide, we need to finalize what is the filter, type of filter, and also what is the design method. So this is the another important section, design method. Either you can design an IIR filter, or you can design an FIR filter. Even in both of these, there are different methods are available. Example, for in FIR methods, there are different design methods like equiripple method, least squares method, windowing techniques, and there are many other methods as well. Similarly, for IIR, you have Butterworth, Chebyshev type 1, Chebyshev type 2, elliptic filters, and so on. Okay, so for the moment, let's keep it simple. Let's design an FIR filter, and you know that FIR filter only has numerator part and it has only zeros. Denominator part is unity, and you know the reason for that, so I'm not explaining that here. So let's choose any method. For the moment, let's choose some uh, window method of designing an FIR filter. And here you can specify the filter order. What is the order that you would like to, what is the order of the filter? So either you can specify the order, you can select, or you can select minimum order. So for the moment, let's select minimum order. And here you can choose what is the window that you are using. Okay, so there are a lot of windows that you can use in windowing methods of FIR filter design. And so for the moment, let's choose the basic one, which is the rectangular window, and we can view that window using this view button, and it will open up the new window showing what is the rectangular window and what is the frequency domain. So you can check the remaining windows as well. Okay, so now coming to this section, here we need to define what is the cutoff frequency. Okay, okay. So for the so here, yeah, what is FS? FS is, first of all, it is the sampling frequency. Okay, you can see from the specifications, it is the sampling frequency, and we have selected the sampling frequency as 500 hertz, and FC is the cutoff frequency. So in our case, we know that the frequency that we want to keep is actually 10 hertz. Okay, because we have defined the signal as sine 2 pi 10t, and hence we have seen from the frequency diagram, or the magnitude spectrum, there at 10 hertz we need to keep, and the higher frequency components we need to eliminate, since we are defining or designing a low pass filter. So we'll keep the cutoff frequency as maybe 10, or roughly maybe 12. 12 is a good value. So let's see what is the design. Once we set these things, we'll just click the design filter, and this algorithm will automatically find a filter design for us, so that the cutoff frequency is 12 hertz. So till 12 hertz it is somewhat unity, and after that it will be 0. So yeah, this is performing reasonably good, but what ideally we want is to be uh, yeah, the magnitude to be 0 dB till 12 hertz, and after that it must reduce. Okay, so this is fine, or let's keep it 10 itself. Let me try to design it once again. Okay, so there is not much change. Okay, so once the filter design is done, there are different options here. I am not going into details of any of these options. Here you can see so this is the magnitude spectrum. You can see the frequency spectrum. You can see both magnitude and frequency spectrum together. You can see the impulse response. This is an FIR filter. So you can see the symmetric nature of FIR filter, which corresponds to linear phase. You can see the step response. You can see the poles and zeros. Okay, so these are the zero locations, and so on. So these features are there. So let's see the magnitude spectrum for the moment, and we have designed the required FIR low pass filter. Now what we need to do is we need to take this designed FIR filter to the workspace. Okay, so that we can use that designed filter in our main program. Okay, so what we need to do is go to the file, export. So click on export, and there are different options. You need to export it to the workspace and export as. There are different options for exporting. So for the moment, let's keep as export as coefficients. And we know that since it is an FIR filter, there is only numerator, so we can define the numerator name, and suppose let's define it as capital NUM. And if you click export, you will see that that particular variable will come in the numerator, okay, which is the numerator coefficients of FIR filter that we have designed. Okay, so now let me minimize this. So let me try to write NUM in the command window to see what is this filter. So you can see that these are the coefficients of filter. Now how to see this, the transfer function of this particular filter. So in order to see the transfer function of filter, you can use the transfer function command, that means TF. You need to define the numerator and denominator. Here numerator is NUM, which is the numerator coefficients. What is the denominator for FIR filter? It is 1. So numerator comma denominator comma, then you need to define the sampling period. Here I have defined sampling period as capital T. So if you define sampling period also in the function TF, it will generate the transfer function in Z domain. Okay, so let me try to run this. Okay, so this is the transfer function of FIR filter that we have defined. 0.08731 is raised to 10. So it's of the order 10. Okay, so this is the way how to obtain the transfer function of the filter. What you need to do is design the filter in the app, export it to the workspace, and use the function TF, numerator comma denominator comma the sampling period capital T. So this will give the sampling the transfer function. Please remember that since this is FIR filter, we have the denominator as 1, while for IIR filter we need to define numerator as well as denominator. Okay, while exporting we can see both numerator and denominator. I will explain that after going through the FIR filter. Okay, fine. So let me go back to the code for the moment. Yeah, so don't worry about this command for the moment. So this command is for the IIR filter. I will come to that later. And this is the command that I have defined now. So sys is equal to, so I use this as the to define a system, numerator comma 1 comma t, which will define the transfer function. And now now we need to do is we need to filter the signal. So in order to filter the signal, we can use the command filter. So this is the command to filter a signal. Y is equal to, so y is the filtered output, y is equal to filter, and we need to define the transfer function. Here we have denominator as 1, so numerator comma denominator comma x. What is x? X is the noisy signal that we have defined initially. So if you do this, y is actually the filtered signal. So let me try to run this. Yeah, so now also we haven't plotted the filtered output. That is why it is still showing the noisy signal and the frequency transform of the noisy signal. Now in order to plot the filtered output, we are using a similar command similar to the previous one. So I have defined the second figure, figure 2, and I am plotting k comma y, which is the plot of filtered signal. In order to find the frequency transform or Fourier transform, I am using the command FFT, and I am plotting the magnitude spectrum as well. Okay, so as a second figure, I am plotting the filtered output as well as the magnitude spectrum. So let me try to run this. So you can see that two figures have come. Yeah, perfect. So the first figure, this figure is the uh, the noisy signal which has noise in it, and this is the magnitude spectrum of the noisy signal, and it has noises here. And figure 2, this is the filtered output. You can see that we are almost getting the perfect output that we require. Good. So that means this FIR filter is performing well. Okay, so this is about the general design of FIR filter. Now let me tell about IIR, and after that, yeah, I'll wind up. So in order to design the IIR filter, so let me again switch to the filter design. I have taken it from this. So if you minimize it, it will go to this panel, and if you click on the middle, yeah, on the top one, we can open it once again. Now let me try to design a low pass IIR filter, maybe Butterworth filter for the moment. Okay, so I have selected IIR here, and I have selected Butterworth here, and here you have an option to see the filter specifications. Okay, so it was showing the magnitude spectrum, but I would like to see the frequency specifications of IIR Butterworth filter. Let me check if Shebishev. Okay, yeah, different options are there. So for the moment, let me select the Butterworth filter, and here I'll select it as the minimum order for the filter order. So these are the specifications that I need to specify for designing a Butterworth IIR filter. So if you see, since it is a low pass, that is why it is having a 0 dB till f pass, and it is very low after f stop. Okay. If it was high pass, so suppose if you select high pass, you can see that it is changing. Okay. So for the moment, let's stick to low pass filter. And there are four specifications are there. One is F pass, which is the pass band frequency. F stop is there, which is stop band frequency. A pass, which is pass band attenuation, and A stop, which is stop band attenuation. So there are two bands. One is pass band, which passes the frequency, and there is another band which is stop band. Okay, in pass band, the frequency will be passed through, and in stop band, the frequency will be attenuated. Okay, so F pass is pass band frequency, F stop is stop band frequency, A pass is pass band attenuation, A stop is stop band attenuation. So we need to define these things. So Fs is the sampling frequency, which is 500. F pass, what is the pass band frequency? So we require the pass band frequency to be 10 hertz, and F stop, it can be something towards the right of F pass, and A pass and A stop can be 1 and 80. So this is A pass, which is a small value, and A stop, which is the attenuating value, it can be 80 dB. And if you click on design filter, you will see that a filter is designed with this particular frequency magnitude spectrum. That means at 10 till 10 hertz, maybe we'll give it maybe at 12 hertz. So I'll design it once again so that the frequency spectrum moves little towards the right. Yeah, so it is 12 hertz, and the stop band frequency is 40 hertz, and these are pass band and stop band attenuation. Once we have designed this filter, we can take this filter uh, by clicking on export to the workspace. So while exporting, so this is the only change. So in FIR filter, there was only numerator, but in IR filter you have numerator and denominator, but we don't have the numerator and denominator specified here. But on the other hand, we have something called as SOS metrics and scale values. So if you see, yeah, here the structure that is used for IIR filter design is direct form 2 second order sections. So SOS stands for second order section. So in Matlab, IIR filter is designed as second order sections. Okay, you know what is a direct form 2. So in direct form 2, it is designed as second order sections. So we have this SOS metrics and gain values. Anyway, we will export these to the workspace, and from workspace we will get the numerator and the denominator. I will show you how to get the numerator and denominator. So you click on export, so that capital SOS and G. So here is capital SOS and the gain G is there. Once we have SOS and G, we can use the command. So I'll define numerator comma denominator, and we'll use this particular function. So please remember this function SOS to TF. Okay, so you can see that it converts digital filter second order section data to a transfer function data. In bracket, you need to define SOS comma capital G. So SOS and a capital G is there in the workspace, and this particular function will give the numerator and denominator. So I'll try to run this, and it is computing the numerator and the denominator coefficients. So that is this particular command that I have used previously. Oh, I think there is a problem. The problem is that we have already defined the numerator here. So what I'll do is I'll try to clear the workspace. Is that working? No. Okay. So I'll try to run this once again. What the problem is that I need to delete this. Okay. Okay, I have uncommented this particular line, but before that I need to define the I think it got stuck up. So let me try to reload this page and see what is happening. Yeah, so these things can come up. Okay, so the filter is, so let me once again define the filter as low pass. It is Butterworth 512, 1 and 80. That's fine. And design the filter. So that is all perfect. Now let me clear the, sorry, let me, so is the numerator variable there? No, it is not there. Okay, SOS is there, capital G is there. Okay, so I'll use this particular command. Yeah, now it is fine. So I'll show the numerator and denominator polynomials. So these are the coefficients of numerator and denominator. Once you have the numerator and denominator, you can use transfer function TF numerator comma denominator comma capital T to get the transfer function. So you can see that it's a ninth order transfer function. Okay, so let me go back to the code. So this particular line will give the numerator and denominator coefficients. Once we have the numerator and denominator coefficients, we'll get the transfer function by using TF, and instead of 1 we now have the denominator, and in order to do the filtering we'll use this denominator. Okay, rest of the things are the same, there is nothing different. Now let me try to run this. You can see that the figure 1, which is a distorted figure and with the magnitude spectrum given below, figure 2, which is a filtered out signal, which is the filtered output, and this is the frequency spectrum. Okay, and the transfer function of the filter is given by, and we have defined it as cis. So if you use cis, you will get the transfer function of the filter. Okay, so I hope you got some idea about filtering or designing a filter in Matlab. So please work out different types of do try to design different filters and see the responses in Matlab. And yeah, so with that I'm stopping. Thank you.